This video is for matrix algebra. The first thing we need to start off with is the definition of matrices. Matrices, or one matrix, is actually a rectangular array of numbers, and these numbers are called elements. They are actually in a bracket, and they are denoted with a capital letter. Elements are denoted with the symbol A, I, J, where I and J represent the row and column, respectively. So let's take a look at some examples of matrices and talk about their dimensions. So let's start off with a 2 by 2 matrix, 5, 0, negative 6, 1. I call this a 2 by 2 matrix because we can see that it has 2 rows and it has 2 columns. So this is what we call a 2 by 2 matrix. We also call this a square matrix. So anything that has the same number of rows and the same number of columns is called a square matrix. So let's take a look at this matrix. We have 6, negative 2, 4, 4, 3, 5, 8, 0, 1. So you can see that the matrix that we have here is a 3 by 3 square matrix as well. Remember, rows are the horizontal and columns are your vertical columns. Let's try another one. There's some special type of ones. For example, 1, 0, 3 has the dimensions of 1 row and 3 columns. Sometimes we call this one a row matrix because it only has 1 row. Likewise, we might have something that looks like 5, the square root of 2, negative 3. This one actually has 3 rows and 1 column. So sometimes we call this guy a column matrix. Let's take a look at some more. Another example of a matrix might be 5, 0, 4, negative 6, 1, 5. And we can see that this one actually has 2 rows and it has 3 columns. 1, 2, 3. Notice also that the number of elements inside of our matrix is equal to the multiplication of rows and columns. So this one has 6 elements. Remember, elements are those numbers on the inside. We can also have special matrices. Here is what we call a zero matrix. And that's because it has all zeros as their elements. And notice this is a 2 by 2 matrix. Last but not least is a special matrix called 1, 0, 0, 1. Again, this is a 2 by 2 matrix, and this one's actually called the identity matrix. And we'll talk more about it later. Let's try example number 1. Our job is to add and subtract matrices. In order to do this, the matrices must have the same dimensions. So take a look at matrix A. Notice I have a capital letter, so we can denote that that is a matrix. And we also have matrix B. Notice that the dimensions of them, so let's take a look. Matrix A has the dimensions of 2 rows and 3 columns. Matrix B also has 2 rows and 3 columns. Because the dimensions are the same, we are able to add them. In order to add them, think about adding corresponding parts. In other words, if I look at the first position of A, that's a 2, and I'm going to add the first position in B, a negative 3. And then for the second one, so this is in the first row, second column is a 4, and the first row, second column is another 4. And for the last one, the first row, third column is an 8. First row, third column is a 0. I'm going to do the same thing down here. So second row, first column is a 0. Second row, first column is a 6. So I'm going to add those two together. I'm going to add the 1 and the 8. And I'm going to add the 2 and the 2. So what we notice is that our end result will be negative 1, 8, 8, 6, 9, and 4. Also notice that our answer here also has a 2 by 3 dimensions. So notice that we need the exact same dimensions, and we will get the exact same dimensions when we're done. Now let's try subtracting matrices. One of the things that you might want to do is to actually think about this as matrix A plus a negative B matrix. When I do that, we can see that we're going to get matrix A from our original matrix, which was 2, 4, 8, 0, 1, 2, and we're going to add the negative B. In other words, I'm going to change everybody's negative to a negative number. So negative 3 becomes a positive 3, 4 becomes a negative 4, 0 still 0, negative 6, negative 8, and negative 2. And now we're back to adding. Remember, we're going to add corresponding locations or corresponding elements. So I'm going to add the 2 and the 3. I'm going to add the 4 and the negative 4. I'm going to add the 8 and the 0. I'm going to add the 0 and the negative 6. I'm going to add the 1 and the negative 8. And I'm going to add the 2 and the negative 2. Let's try using different operations for matrices. One of the ones that we want to use is actually scalar multiplication. Scalar multiplication is when we multiply the matrix times a constant. So matrix multiplication, if I have 4c, what I'm doing is I'm going to get 4 and I'm going to multiply it times 9, 0, negative 3, and 6. So when we do this, what happens is we actually multiply everybody inside by that number. So I'm going to get 4 times 9 is 36, 4 times 0 is 0, and I'm going to get 4 times negative 3 is negative 12, and 4 times 6 is 24. So this blue matrix represents 4c. Notice that C had a 2 by 2 dimensions, and my answer also has a 2 by 2 dimensions. Let's talk about subtracting as well as multiplying with scalar constants. So in other words, let's rewrite 3a, and I'm going to write that one in blue. And then what I'm going to do is I'm going to do negative 2b, and then I'm going to add them together. In blue, I'm going to write 3 times a, so I'm going to get my A matrix, and I'm going to multiply everybody times 3. So I get 9, 3, 15, negative 6, 0, 18. Then I'm going to get everybody in B, and I'm going to multiply by a negative 2. So I'm going to get negative 8, negative 2, 0, negative 16, negative 2, and positive 6. And now we can see that we're just back to adding two matrices. And I'm going to do location, location, location. When I add these, I get 1. When I add, I get 1. When I add, I get 15. When I add, I get negative 22. When I add, I get negative 2. And when I add, I get 24. So notice my new matrix has the exact same dimensions as A and B, and we were able to use scalar multiplication as well as addition in order to solve this problem. Now let's go into matrix multiplication. In order to do matrix multiplication, we actually have to have the number of columns of the first matrix equal the number of rows of the second matrix. So here's a good way to remember it, that if I write down my dimensions of my first matrix and I write down the dimensions of my second matrix, these two numbers in here actually have to be the same. If they are not the same, so these two numbers have to be exactly the same. If they're not the same, then we cannot do matrix multiplication. If these two do equal to each other, then notice that my answer will actually have the dimensions of these outside numbers. it would actually have the number of rows of the first matrix and the number of columns of the second matrix. So that's what it's showing you here. So let's try that by multiplying matrix C times matrix A. First we got to check to see if we can even multiply, and then we'll actually do the multiplication. So here's matrix C and matrix A. So for matrix C, we know that this is a 2 by 2 matrix, and matrix A is a 2 by 3 matrix. Since we have the same numbers on the inside equal to each other, then I know my answer is going to be a 2 by 3 matrix. So we're going to have a 2 by 3 matrix. So let me show you this. 2 by 3 matrix means I have 2 rows with 3 columns. So I'm going to put blanks in there. So that's how big my matrix is. And then let's think about what the position is. So this position is the 1, 1 position, meaning that it is row 1, column 1. So that means I'm going to use row 1 and column 1. What I'm going to do is I'm going to multiply the very first element of each one of those together. That's going to give me 27. And I'm going to add what I get when I multiply the second numbers in each one, which is 0. So we're going to find that to be just 27. Now take a look at this element. This is still in row 1, but in column 2. So that means we're going to use row 1, but we're going to use column 2. We're going to multiply the very first element times the very first element in each one of those row and columns. So I'm going to get 9, and then I'm going to add the multiplication of the second elements to each other, which is 0. And when we finish adding, it's equal to 9. I don't have to do these in order. In fact, I can take a look at this one down here, which is in the second row, third column. So I'm going to use the second row and the third column. And now I'm going to multiply the first element times the first element. That gives me negative 15. And I'm going to add the second element times the second element, which is 36. So I'm going to add those two numbers together and get what value goes right there. I'm going to go ahead and continue in finishing up my matrix. So what I like to do is I like to look at row 1 and then do all the columns. So we already did column 1, column 2, so now let's do column 3. So when I multiply, I'm going to get 9 times 5 is 45, plus 0 times 6, which is 0, so I'm going to get 45. Then I'm going to go to the second row, so I'm going to come down here to the second row and do the first column. When I multiply, I get negative 9 plus a negative 12, which is going to give me a negative 21. Then I'm going to use my second row and my second column and multiply, and I'm going to get negative 3 plus 0, which is negative 3. And that's what goes right here. And we have finished multiplying those two matrices. So let's give you a chance to do it as well. So here's example number 2 in order for you to multiply matrices. So the first thing we need to do is to make sure that when we're multiplying matrix A, and matrix A is a 2 by 3 matrix, and matrix B is a 3 by 2 matrix, that the numbers inside are equal to each other, and my answer will be a 2 by 2 matrix. So let's do a 2 by 2 matrix. The 2 by 2 has 2 rows and 2 columns. So we only need to find 4 numbers. If we take a look at the very first one, this one right here, it is in the 1, 1 position, which means I need to use row 1 and column 1. And then location, location, location. I am now multiplying 2 times 1, 1 times 2, and 3 times 3. And when I add them together, I get 13. Then I do the same thing for this element. It says use the first row and the second column. And now I'm multiplying 2 times 0, 1 times 1, and 3 times 2. And I add them and I get this number here. This is in the 2, 1 position, so we're going to use row 2 and column number 1. When I multiply, I get 1 times 1, negative 1 times 2, and 0 times 3. And I add those together. And finally, for the last one, remember this is row 2, column 2, so I'm going to use row 2 and column 2. And I multiply, I get 0, negative 1, and 0. So there's our answer for our matrix of A times B. Now let's try multiplying B times A. For matrix B, notice we have a 3 by 2 matrix. For matrix A, we have a 2 by 3 matrix. Notice that we can multiply them, and our answer is going to be a 3 by 3 matrix. So the big study about this is I wanted to make sure that we understood that matrix A times B is not the same thing as B times A. We can clearly see that here we're going to have a 3 by 3 matrix, which means 3 rows and 3 columns. So there's no way they're going to be the exact same matrix. In order to be the exact same matrix, they have to have the same dimensions as well as the same elements in the correct location. So I'll leave this up to you to see if you can multiply and find those numbers. Let's go on and talk about the identity matrix. We kind of glanced at that at the very beginning when we were talking about different types of matrices. But now let's talk about the identity matrices. First of all, they are square matrices that have 1s on the main diagonal and 0 everywhere else. So let's take a look at some example. Sometimes we'll call them like this as a big I with 2 by 2 to denote that this is a 2 by 2 matrix, which 1s on the main diagonals and 0s everywhere else. So for a 3 by 3 matrix, remember we're going to have 3 rows, and each row and down the middle is going to have 1s and then 0s everywhere else. This is a 3 by 3 identity matrix. And you can continue doing this for a 4 by 4, 5 by 5. But one of the biggest things we do want to note is that if you multiply the matrix A times the identity matrix, or the identity matrix times A, that you'll actually get the matrix A. This is what we call the identity property. If A is a square, non-singular matrix, and we'll talk more about what non-singular means, when that happens, then we can find that A times A inverse, that's this guy right here, is equal to A inverse times A, and the result will be the identity matrix. So notice I mentioned that A inverse is denoted by A to the negative 1 power. That means inverse. So the big question should be, why do we even care about the inverses? What we can do is multiply and see what this actually gets me. So I'm going to show you that we would multiply row 1. Remember, this is a 3 by 3 matrix. This is a 3 by 1 matrix, so we can multiply, and we do get a 3 by 1 matrix. When we multiply, we're going to see that I get 1x plus 1y plus 0z, and that's equal to 3, the same thing that's right here. That we do the same thing for the second row. In the one column we have, I get negative x plus 3y plus 4z is equal to negative 3. And the last one, the last row and the one column, I get 0x plus 4y plus 3z is equal to 2. So we'll talk more about this later, but what we find is that we can actually write our systems of equation into matrix form. So if we know that this is what we call a coefficient matrix, these are the coefficients of my x, y, and z. This is what we call our variable matrix, because it has all the variables in it. And this one right here we actually call the answer column. So now that we have all of these, we notice that we have matrix A times matrix X, our variable matrix, is equal to our answer column, that if I multiply both sides by A inverse, if I do that, then on the left side we're going to find that that's just equal to the identity matrix times X is equal to A inverse times C. Or we just found out by the identity property that this just means that I'm going to get X is equal to A inverse times C. So this is yet another way to solve for X, Y, and Z. So let's try that by using our next example. So notice what they say, that we have a system. Here's our system of 3 equations. If we look at each one of them, so the coefficient for X is 1, the coefficient for Y is 1, and since there's no Z, we put a coefficient of 0. In our answer column, we'll have a 3 at the very top. And then in the second equation, we're going to have negative 1x, positive 3y, positive 4z, and a negative 3 in my answer column. For the last one, I have no x's, so that must be 0x plus 4y plus 3z is equal to 2. So notice I am writing my system of equations like this, that if I had x, y, and z and multiplied it times my coefficient matrix, then I would have the same thing with my answer column. So now what we're going to do is I give you, notice this is matrix A, I give you matrix A, and I also give you the inverse. Well, remember what we just finished writing, that if you want to find X, or all the variables, our matrix, our variable matrix, then get A inverse and multiply it times the answer column. So we're going to get A inverse and we're going to multiply it times the answer column. So let's first make sure that we can do that by looking at our dimensions. Notice that this one has a 3 by 3 matrix and this one has a 3 by 1 matrix, so we can multiply and get a 3 by 1 matrix. So let's see what we get when we do that. So we're going to multiply row 1 times our answer column. So I'm going to get 7/4 times 3 plus 3/4 times a negative 3 plus negative 1 times 2. So we've got to add all these. So this is where our handy dandy graphing calculator comes in handy, but we should be able to do this even without that. So that becomes 21/4, negative 9/4, plus a negative 2. So when I add those two together here, I'm going to get 12/4. That's when I add these two, minus 2, and we can see that's going to be 3 minus 2, which is equal to 1. So that's that first one. Now let's multiply row 2 times our column. That's negative 3/4 times 3, another negative 3/4 times a negative 3, and 1 times 2. So I'm going to get negative 9/4. Over here I'm going to get these two negatives cancel out, so I get plus 9/4 plus 2, and we can see that that equals to 2. So let's do the last one. We're going to multiply row 3 times my answer column. These are all integers, so I think we could do this in our head. So 1 times 3, 1 times negative 3, and negative 1 times 2 is a negative 2. So we get negative 2 here. So what does this mean? This means that my variable column, which is x, y, and z, is the same thing as 1, 2, and negative 2. What that means is that x is equal to 1, y is equal to 2, z is equal to negative 2. So our solution set to this consistent and independent system would be the triplet 1, 2, negative 2. And that concludes this video.